acid-base neutralization, as well as go over an overview of the titration process. We're going to continue tomorrow doing more titration problems and learning more about those details. We'll get an overview of it today, and we'll talk about the neutralization process. These two topics are both still included on the AP test. Titration in particular, and doing titration problems is an important topic. An acid-base neutralization is definitely a big idea when talking about acids and bases, because as you know, many acids and bases are harmful, and so when we're working with them, once we're finished, we need a way to dispose of them safely. And the go-to process is neutralization. When we say we're neutralizing an acid or a base, what that means is we're reacting it with a very precise amount of an opposite acid or base to react all of the hydrogen and hydroxide ions. So for example, if we had an acidic solution of perchloric acid here, to neutralize it, we would need to use up all of the hydrogen ions in solution. We could do that by reacting it with the base. When we mix an acid and a base, the hydrogen and the hydroxide ions react to make water. In a neutralization reaction, we always react one acid and one base. The products are always liquid water and a salt. Note, we don't mean table salt, we mean an ionic compound, a salt, a combination of whatever the other ions were that weren't hydrogen and hydroxide end up here. So once we've done that, we have neutralized our acid and our base. We've got water now. It's perfectly safe. We do have to be very careful with these reactions because we want to have an exact amount. We need to perform very careful calculations because we don't want to add too much base, because then we react all the hydrogen ions and still have hydroxide left over. We don't want to add too little because then we will react all the hydroxide and still have hydrogen left over. We want to add a very exact calculated amount to react all of our acid or all of our base. So let's do an example. Let's say we want to neutralize 50 milliliters of a sodium hydroxide solution that has a concentration of 0.0875 moles per liter. So that's our starting solution, and to neutralize it, we've got a solution of perchloric acid, and we have a solution that has this concentration, 0.115. So we need to know how much of this we need to add to have a perfectly neutralized solution. Now, if these were equal concentrations, this would be easy, right? If these were of equal strength, then we would just need to add the exact same amount to balance it out. But they're not, so we'll have to figure out how many moles of hydroxide ions we have so that we know how many moles of hydrogen ions we need to add to neutralize it. So, to walk through this problem, step one is writing a balanced equation. We will need the relationship between the reactants here to work this problem. And so we've got our balanced equation. When writing it, the key to remember is that when we react an acid and a base, our products are always water and then the other ions in a salt. So that's step one. Step two, we need to know the initial amount of our reactant. So we know that we started with a solution of sodium hydroxide, and we know the concentration, we know the moles per liter, and we know the volume. So if we multiply our moles per liter by liters, we will get the total number of moles of sodium hydroxide we have in solution. And then, thanks to our balanced equation, we can use stoichiometry to find out how many moles of perchloric acid we need to add. These are 1-to-1 in their coefficients. For every 1 mole of sodium hydroxide we react, we need to consume 1 mole of perchloric acid. So this is nice and easy here. If we want to neutralize 0.004 moles of sodium hydroxide, we need to add that exact same amount of perchloric acid. So we know how many moles we want. We just need to find out what volume we need to measure out. So we know our concentration. We know how many moles we want. So we take our moles, divide by moles per liter. It gives us the volume of solution in liters that we need to add to neutralize this reaction, this base completely. All right, now with that concept of neutralization, we can apply it in a very specific way to give us the process of titration. And you may have talked about titrations last year. I'm sure you did. Titrating a solution is an analytical technique. We use it to calculate the concentration of an unknown solution. So this is what a setup would look like. We have our unknown solution in a beaker here. In our beaker, we've got our unknown solution and an indicator. And recall from previous lessons, an indicator will change color when a very specific pH is met. So the moment an indicator changes color, we know something about the ratio between our hydrogen and hydroxide ions. And so we want to be as precise as possible when adding solution to our unknown, because we want to know the exact moment the indicator changes color, because that will tell us exactly how much of this acid or base was added before we hit that threshold pH. And so our unknown is here. Up here in this apparatus, this is called a burette. Up here is a standard solution. We know the concentration, we know the composition. In this picture, it's sodium hydroxide. So we've got an unknown acid concentration down here. We're going to slowly add base to it until the indicator tells us we've reached, in this case, an equivalence between the acid and the base ions. The reason a burette is used is because it allows you to add solution drop by drop. It's extremely precise, and that's exactly what we want. We don't want to add all of this at once and go straight from clear to pink. We want to go drop by drop so we can see the exact time we get the color change. One important little minor detail to keep in mind when you do these in the lab is that burettes are typically labeled downwards. So what I mean is the small numbers are up here. We start here with 5, 10, 15, 20 milliliters and go down, because what we care about is how much solution was added. So that allows us to start at 1 or 0 if we're really good, and we start at the 0 point. Then we can read the values going down and know how much solution has been added. So if we took a reading here of 40, we would know that we added 40 milliliters to our beaker. Here's just another picture showing the titration setup. Once again, very important to go slowly on these. You need to add drop by drop so that we know the exact volume at which we hit our pH. So to talk about this step by step, we're always adding solution from the burette. So we're always going from the burette to the beaker. We're always reacting one acid with one base. And we use an indicator to show when an exact stoichiometric reaction has occurred. So we pick our indicator very specifically to show us when we've reached a certain pH value, when we've reached a certain ratio of hydrogen to hydroxide ions. What's happening in our beaker can be shown by this net ionic equation. Remember, net ionic equations leave out any bystander ions and only include the ions actually reacting so we can see the reaction of interest. So for our titration, what we care about is that the hydronium or hydrogen ions are reacting with hydroxide ions to make water. And then if we've chosen an indicator, such as phenolphthalein, which is the pink one in the past slides, we've chosen an indicator at which gives us a very specific pH. And in many cases, we'll choose one that's at an equivalence point. And when we say equivalence point, we mean that the moles of the hydronium, or the hydrogen ions, are equal to the moles of hydroxide. We've reached an equivalency here. We've got an equal number of acidic ions and basic ions. They have equaled out. Often, a common standard that we'll use when standardizing bases is the monoprotic acid KHP. Monoprotic, remember, means one proton. KHP is an acronym for potassium hydrogen phthalate. It's not a chemical formula, it's an acronym. Its chemical formula is actually this down here. This one's used because it's extremely convenient. 1 mole of KHP will always yield 1 mole of hydrogen ion in solution. It's monoprotic, and it dissociates in solution to give us 1 hydrogen ion. And we're going to do an example with it on the next slide. The other piece of information we need about it is its molar mass. Of course, you could calculate this off the periodic table, but for the purpose of the next problem, I'm including it here. It's 204.22 grams per mole. So let's look at an example. So we're preparing a solution of sodium hydroxide. And we're going to perform a standardization of the solution, meaning we're going to titrate it and calculate its exact concentration. We're using KHP as the standard, as our known concentration solution. And we are looking to determine the exact concentration of sodium hydroxide that was in this solution. So in this case, what we're going to do is we're going to have this KHP in our beaker. So we've put the KHP in our flask, in our beaker, and we've measured the mass of the flask with the KHP in it and the mass of the empty flask. So by subtracting these two, we'd know our total mass of KHP, and so our total moles of KHP we could convert. And what we're going to do is we're going to put our solution in the burette. This way, we can calculate a very precise volume that was added to the KHP and know exactly how much of this was added before we reach the equivalence point. And knowing that, we'll be able to know how many moles of hydroxide we had in that volume. And we'll walk through this. So the data we can collect from our titration is, again, the mass of KHP we started with. So we'll have that. We'd have an initial burette reading. Again, don't let this confuse you. The small number is the initial reading because the burette is labeled with the larger numbers towards the bottom. So we start at this point on the burette and we add solution from the burette to our beaker until the final reading is about 30. So the amount of solution added to our beaker is the final reading minus the initial. So here's our next pieces of data. As I said, we do final minus initial in both these cases. We know the mass of KHP in our beaker, and we know the volume of sodium hydroxide added. And so our goal was to calculate the concentration of the hydroxide ion in the sodium hydroxide solution. Concentration means molarity. That means we're doing moles per liter. Total moles of hydroxide over total liters of sodium hydroxide solution. And so, if we've reached the equivalence point, our moles of hydroxide must equal our moles of KHP at the equivalence point. These are equal. Moles of hydroxide would equal moles of hydrogen, and we know that we get 1 mole of hydrogen from each mole of KHP. So if we know how many moles of this we added, which we can calculate, and we will on the next slide, we would know how many moles of sodium hydroxide were added. And then we want the liters of sodium hydroxide. And that's given by our total liters titrated. Remember, we don't care what the volume of this was. We care what the concentration of sodium hydroxide was to begin with. So we want to know how many moles were added and how much solution we had to add to get that many moles. So that's the difference in our burette reading here. So to plug in numbers, we've got our mass of KHP. We calculated that by weighing the flask. We're going to convert that from grams to moles using the molar mass. And then we know that every 1 mole of KHP reacts with 1 mole of hydroxide ion. So we know how many moles of hydroxide ions we have present. We've got total moles, which means we just need to divide by our volume. We know how many milliliters of sodium hydroxide we added, and we just need to convert that to liters. And so we calculate that our concentration of hydroxide ions in the solution was about 0.005. And since sodium hydroxide is a strong electrolyte, we know it completely dissociates in solution. We know that however many moles of hydroxide we have must have come from the same amount, the same initial concentration of sodium hydroxide. And so we know the concentration of our starting solution. All right. One other thing to keep in mind when we talk about titrations is what we're going to introduce as the common ion effect. And this effect is used to create buffers, if that term's familiar to you. Let's talk about the common ion effect first. So consider the solution below. We've got acetic acid dissolved in water, and we know acetic acid is a weak acid, so it will partially dissociate. It will create some hydronium ions and some acetate ions, and these ions will be in equilibrium with the rest of the undissociated acid. So if we've got this solution and it's sitting at equilibrium, let's say we went back and we add some additional acetate ion. We know from our last unit that this is going to shift the equilibrium. We added product. We added acetate ion over here. The system acts to undo our change, and so it will use up some of that added ion and produce more reactant. It will shift our equilibrium back in this direction. To put that formally, the common ion effect says that the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So to go back to that reaction, normally, if we just had the acetic acid by itself in solution, it would dissociate a certain amount. It would have a certain percent ionization. But if instead we tried to dissolve it in a solution that already contained the acetate ion, say first we put sodium acetate in, sodium acetate contains an alkali metal, it's a strong electrolyte, it completely dissociates. So we already have some acetate ion. Now when we add acetic acid, we get less dissociation, less ionization, because there's already some here. The equilibrium has been shifted to the left towards the reactants. Let's see an example. So in this example, we are trying to calculate the fluoride ion concentration and the pH of a solution that has a concentration of 0.2 molar hydrofluoric acid and 0.1 molar hydrochloric acid. Hydrochloric acid is one of our strong acids. We know it will completely dissociate in water, and so we will have 0.1 moles per liter hydrogen ions and 0.1 moles per liter chloride ions. Hydrofluoric acid is a weak acid. We would need to use its acid dissociation constant to figure out how much hydronium and how much fluoride ion concentrations we have. Now typically, if we just had hydrofluoric acid, we could just use this information to calculate what these equilibrium concentrations would be. But in this case, we've got a solution in which we already have some hydronium ions, thanks to the hydrochloric acid. So we already have some of this value, which means this equilibrium is going to be shifted back towards the hydrofluoric acid. Let's make an ICE table to show this information. So the hydrochloric acid is completely dissociating. We don't need to write an equilibrium for it. The hydrofluoric acid is going to be in equilibrium with the hydronium ion and its conjugate base. So when we fill in our initial conditions, we know how much hydrofluoric acid that we're adding, 0.2 moles per liter. We know our initial concentration of hydronium ion is not 0 because we've already added some from the hydrochloric acid. The initial concentration of hydronium ion is equal to the amount of hydrochloric acid added because the hydrochloric acid dissociates completely, and so we already have an initial concentration of this part of the products. We still have 0 initial fluoride ion because in our initial condition we don't know how much is going to dissociate yet. And then we'll plug in our change. Just like before, we're not sure how much this is changing, so we'll let it equal some value x. We will assume that some of the hydrofluoric acid is going to dissociate, so this concentration is decreasing by some amount x. And however much it decreases by, the concentration of both of the products must increase by that amount. And so we can write an equilibrium expression for each of these. Notice the assumption we made here to make our math easy. We're going to assume that x is very, very small compared to these initial numbers. So small that subtracting or adding it wouldn't truly appear in our numbers. It wouldn't really have an effect after rounding. And so we've got these numbers. These are what we'll plug into our equilibrium expression. We still have products over reactants, so our product concentrations over our equilibrium reactant concentrations. And now this is we're perfectly capable of solving this for x. We'll multiply both sides by 0.2, divide both sides by 0.1, and we've got a value for x. And notice this x is small compared to these initial values, and so our assumption is valid. We can keep that number. We plug x in to get our equilibrium concentrations of these values. So we know our final concentration of fluoride ion is going to equal x. We can calculate our final concentration of hydroxide ion. Again, notice here explicitly why this assumption works. When we add x to 0.1, we'd get 0.1014, which would just round back to 0.1. We don't see this change because it is so small compared to x. So again, our assumption was valid. This is our concentration of hydronium ion, so we can plug that into our pH formula to calculate our pH. This common ion effect is used in a class of substances called buffers. Buffers are solutions of a weak conjugate acid-base pair, and they're useful because they resist pH changes. Even when a strong acid or base is added, they've got these common ions in them already, and they can buffer the solution. They can make it more able to dissolve or take in that acid or base without actually increasing or decreasing in pH. And we'll go through some examples to see this play out. So To start to look at buffers, first we're going to write some general reactions that occur when a buffer solution containing the weak conjugate acid-base pair, hydrofluoric acid, and its conjugate base, the fluoride ion. We're going to write the reactions that occur when an acid is added to this solution and when a base is added to this solution. So go ahead and write those out. Here's what happens. So when an acid is added, the hydrogen ions from the acid react with the conjugate base in the solution with the fluoride ions to make more hydrofluoric acid. So instead of these hydrogen ions going towards increasing the pH, they're reacting with our buffer solution to make more of this compound. So our buffer solution is preventing a change in pH. When a base is added, it reacts with the hydrofluoric acid compound to make more of the conjugate base and water. So again, instead of the hydroxide ion going towards changing the pH, it's reacting with our buffer solution. Here's another way of representing this. So here's our initial solution. This is our buffer solution. We've got equal amounts of our weak acid and its conjugate base. And when a small amount of hydroxide is added, so when another base is added into here, the OH reacts with the hydrofluoric acid to make more fluoride ions and water. And so we don't see as big of a pH change as we might have without the buffer solution. Same thought process for when the acid is added. If an acid is added, some of the hydrogen ions react with the conjugate base, the fluoride ion, to make more hydrofluoric acid compound. And so again, we don't see as big of a pH change because we have just made more compound. Let's think about a calculation here. So we've written out just a general equilibrium expression for the dissociation of any acid here, a hydrogen bonded to another element, any acid dissolved in water to produce hydronium ions and its conjugate base. And the dissociation constant for this would be the product concentration over the reactant concentration. We're going to rearrange that slightly. We're just pulling out the hydrogen ion or hydronium ion concentration out front. And then we're going to take the negative log of both sides. And the reason we pulled this out front is that, remember, when you are working with logarithms, if you've got the log of two things being multiplied, we can split that into two logarithms that get added together. So we're rearranging to create this equation. We took the negative log of Ka, we took the negative log of the hydronium ion concentration, and we're going to add that to the negative log of this whole piece right here. The reason being, we know that the negative log of Ka is pKa. We know that the negative log of hydronium ions is our pH. And we know this is the concentration of our base, the conjugate base. This is the concentration of the acid. We're going to solve this for pH. So we solved for pH by adding the log to both sides. This is known as the Henderson-Hasselbalch equation. This is very useful for us. It'll prevent us from having to do entire ice table calculations or full long equilibrium concentrations, because to calculate pH, we just need our dissociation constant and our concentration of base and acid in solution. Here's an example. We want to calculate the pH of a buffer that has a concentration of 0.12 moles per liter of lactic acid, so this is our acid, and 0.1 moles per liter of sodium lactate, this is our base. And we're given the dissociation constant for lactic acid. Now, Previously, we may have needed to write out a balanced equation, go through an ice chart and equilibrium expression problem. But with the Henderson-Hasselbalch equation, we can just plug those numbers in here. We're solving for pH. We know our dissociation constant. We know the concentration of our base, 0.1. We know the concentration of our acid, 0.2. And so we can just plug those numbers in and let our calculator do the rest. A couple other key terms just to mention briefly. The first one is buffer capacity, which really simply just means the amount of acid or base that a buffer is able to handle. It's the amount that the buffer can neutralize before the pH really begins to change significantly. It's its capacity, its ability to deal with an acid or base addition before you start to see a change in pH. And this will depend on the amount of acid, and it will depend on your composition of the buffer. It'll depend on the dissociation constant of the acid and on the relative concentrations that you're using. So for example, a solution that's 1 molar in this general acid and 1 molar in this addition will have its pH equal to its dissociation constant. Let me go back and show you that. That came from the Henderson-Hasselbalch equation. We had a 1 molar acid and a 1 molar base. The log of 1 is 0. So our pH, when the acid and base are equal, is going to equal our pKa, dissociation constant. Similarly, a solution that's 0.1 molar in this compound and 0.1 molar in this compound will have that same pH, but the first one will have a greater buffer capacity. So they will have the same pH in solution, but this one will be able to be effective for longer. The second term is the pH range, which is also pretty much what it sounds like. It's the range of pH values over which the buffer system is effective. And so it's best to choose an acid with a pKa that's close to the desired pH that we want our buffer solution to work at. Now in practice, just a general rule of thumb, if the concentration of one of the components of the buffer gets to be 10 times the concentration of the other component, the buffer pretty much stops working. It's not really effective past that point. Again, just some general thoughts. When a strong acid or base is added, the result is a neutralization reaction in either case. And so by knowing how much acid or base was added based on the stoichiometry of our equation, we would know how much product was formed, and from that concentration we'd be able to calculate the pH either from our Henderson-Hasselbalch equation or from the original equilibrium expression using our ice table. And here's just sort of a flow chart of how to walk through that kind of problem. An important thing to remember is that when a strong acid or base is added to a buffer, you can safely assume that all of that acid or base is going to be consumed in the reaction. If it's a strong acid or base, then it's completely dissociating. It will be completely consumed. And so this flow chart walks through what that kind of problem would look like. You'd start with your buffer. If you add a strong acid, you've got this neutralization reaction happening. If you add a strong base, you've got this neutralization reaction happening. And you can use stoichiometry to calculate your target concentrations. Once you have those, you can use an equilibrium calculation, either the Henderson-Hasselbalch equation or an ice table, to calculate your concentration of hydrogen ions, which you can use to calculate pH. Alright, we're going to do more buffer calculations and more titration information in the next lesson, but hopefully that was a good intro to this type of problem.